Okay, well, good evening and good morning to some of you. My name is Terrell France. I'm a professor at Harrisburg University, which is located about in the middle of the state of Pennsylvania in the United States. And I'd like to welcome you to this very first meetup for the Philadelphia Harrisburg Quantum Computing Meetup group. Before we get much further, I want to make sure, again, slides are available at that link that we had previously, and I'll also put the link in the chat box for you so you can get that during the talk. And also, again, I'm recording this. This event is our first event for the Philadelphia Harrisburg Quantum Computing Meetup, and we're fortunate to be able to partner with the Washington, D.C. Meetup group, as well as the Columbus, Ohio group. And also we have folks from the Philippines Quantum Meetup group as well. So welcome to everybody. Greetings from Harrisburg. Larry will be giving his presentation from New York City area. You know, I'm really looking forward to this presentation going well. I've seen Larry give a talk at the New York City Quantum Computing Meetup about 2 months ago, and I think you'll enjoy it. Anyway, welcome everybody. This evening should last approximately 60 minutes. It could go a little bit longer depending on questions, etc. To make things smoother, what we'll do is we'll generally hold questions until Larry's finished the entire presentation. But if you do have questions, go ahead, put them into the chat there. And if I see anything in particular that I may or may, you know, a question that's particularly striking, I may or may not stop Larry midstream. It's much better to have a conversation, but we've got quite a few people on the broadcast tonight, so it may be a little awkward. Anyway, if you have a question, put it in the chat box, and if I can get to it, we can get to it, we will. If not, save it for the end, when I'll try to open up the audio if that works out. I'm a new user to broadcasting on Zoom, so I'm not quite sure exactly how everything works here, so we'll just try to wing it tonight operationally. Anyway, there are some events coming up in 2 weeks from tonight. Just booked a speaker on March 30th at 7 p.m. We'll have a similar Zoom session, and that will feature a company called qBlocks from the Netherlands, and they'll be talking about the qBlocks control stack. And so it'll be a real interesting talk about their product, and it's not a sales pitch, but what they'll do is they'll walk through the quantum computing control stack from program all the way down to the control of the qubits, etc. So I'm not a hardware guy yet, so I can't really speak to it, but I think it'll be a really interesting presentation, and that'll be in 2 weeks on Monday, March 30th at the same time here. And I'll get the information out to the various meetup groups. It's looking like, because we're now in the Zoom world around the world, actually be able to have another event coming up on April 13th, as well as one on April 27th. So it looks like instead of being live meetups, we'll be able to do meetups every 2 weeks through the Zoom here. So I hope that works out for you. In 4 weeks, we've got Max Henderson from Rigetti talking about quantum machine learning and such. Anyway, so details will be announced through the Philadelphia Harrisburg Meetup site, and as well as I'll get this information to the other meetup groups as well. I hope you guys all get a lot of information out of these events. I think that since we're all stuck at home, literally around the world, these turn out to be really good opportunities for us to you know, advance our knowledge about quantum computing and anything quantum. Anyway, so allow me to introduce you to Larry Liebovitch, who's a professor of physics and psychology. It's an interesting combination there. He's at Queens College at the City University of New York. So without further ado, I'm going to turn it over to Larry. Larry?
Okay. All right. Thanks very much, Terrell. So let me start sharing my screen so I can show PowerPoint. So it's a pleasure for me to be there at least virtually. These should be PowerPoints. Are those PowerPoints okay? You're in? Terrell?
Yeah, I already muted myself. Yeah, I see it. Looks fine. All
Okay.
yours.
Okay. So as Terrell, I'm going to give the basic introduction to quantum computing. I'll run you through from hardware and software and some of the applications. And as Terrell said, I have appointments in physics and psychology at Queens College and physics at the Graduate Center of the City University of New York. And also I am an adjunct senior research scholar at Columbia University, also in New York. Let me do something else for a moment. Let me see if I turn off, I don't think I need my video actually, because does that kill the slides at your end?
Nope, it's all good, Larry. Looks good.
Okay, fine. I think that will help the bandwidth. So I'm currently teaching a course at the Graduate Center in New York on hardware and algorithms of quantum computing. And if you go to my website, which is listed here, you can actually see the videos and PowerPoints and homeworks and other things of that course, which are all being posted online. And I also teach a number of other courses in astronomy and complex systems and mathematics and physics and psychology. And that's over a number of years, not all at once. And some of the lectures from those courses are on 2 different YouTube channels, including a course I'm currently teaching as well on physics for computer science students with the unassuming name of Smart Physics for Brilliant Computer Engineers Season 2. And my research involves mostly mathematical models and data science of complex systems. Physical systems such as the motion of stars and gas and galaxies, biological systems such as gene regulatory networks, and I work with a group trying to understand the conditions needed for sustainable peace in the world. So quantum mechanics developed over the last 100 years has been one of the most successful theories in physics or anything else. It's allowed us to understand what goes on inside of atoms so that they produce and absorb light, and has been able to predict with great accuracy these lines in the spectra. And it's also been able to make sense out of chemistry, that the periodic table, which orders all these elements and helps us understand which elements bind with each other, quantum mechanics predicts and explains the location of all the electrons in those atoms, the sort of K, L, M, and N, and S and P stuff that you may have had in high school or college. So it explains why chemistry works. And quantum mechanics has also been successful in other things too, in understanding radioactivity and how the transistors in the CPU of your computer work. And strange things happen too in terms of things like superconductivity and many other areas as well. But quantum mechanics has also had spectacular failures. We still don't understand quantum gravity, and we don't understand how molecules really use quantum mechanics. Even though they're built in the atom state together from that, we've been not so clear as understanding how all those pieces fit together to compute or predict the structure and dynamics of larger molecules. But this isn't a bad thing. This is actually an asset that leads us to quantum computers. So Richard Feynman 50 years ago said, if complex quantum systems are hard to compute by conventional computers, which is why we can't do it, maybe we can use quantum computers to compute those quantum systems. And if quantum computers are good at calculating things as complex as quantum systems, maybe they'll also be good at calculating things in other complex systems as well, and so would be very useful. And this just says the same thing. So if we can use quantum computers to compute anything that's as complex as quantum systems, maybe it will have real and valuable uses in cryptology and finance and predicting the weather and understanding biological and social systems. And it's for that reason that many very large companies like Google and IBM and Microsoft and Amazon and Intel and many other companies throughout the world have been interested in quantum computing. And well as a whole wave of startups like D-Wave Systems in Toronto, and many companies usually associated with universities, such as IonQ outside University of Maryland, just on the edge of the Beltway in DC, Rigetti at Berkeley, CRIP here in New York City, and others. And if you go to the website shown here, there's at least 100 other companies that are involved in quantum computers. And the reason why is for some problems, quantum computers could be 10 to the 28th times faster than current computers. And here I've written out 10 to the 28th so you can see all the zeros, and it's got a lot of zeros. But in order to do this requires very different hardware and very different software that we're used to seeing in computers. So the hard part of this is understanding the essential principles of quantum mechanics that set the design features of both hardware and software. And getting the hardware to work without too many errors has actually been a challenge, and creating the software algorithms to solve real-world problems has also been more difficult than maybe expected. So in the everyday world of physics that we're used to, it's the physics of big things. And that world is deterministic, and we can measure things and predict them in certainty. But in the quantum world, the hidden world of the smallest things of atoms and light, all we can measure are the probabilities that something will happen. And once you measure something, that's the end of it. You can't go on using it. It changes forever. So this is the quantum Copenhagen interpretation of quantum mechanics. Before you measure something, there are many possibilities. But when you measure it, you only find one specific result out of a possible set of results. And you can only predict the probability of one of those results, not which one you're going to get. In a quantum computer, the things you measure are called qubits. And before you measure a qubit, it's both a 0 and a 1 at the same time. And that's called superposition. But when you actually do the measurement, you never see anything in between a 0 or 1. Sometimes you do the measurement, you get a 0, and you reset it from the beginning, and sometimes you'll get a 1. And once you measure it, you can never go on using it to compute again. And you can't cheat with this. You can't make copies of a quantum state and maybe say you're only going to measure the copy and you won't mess up the real state. Mathematically, this turns out to be, to do a copy like that would require a quadratic operation, and quantum mechanics is limited to linear operators. And you can understand this from the physics as well, because if you could make multiple copies of things, in some of those you could measure their position, in others you could measure their momentum. And that would, and you could therefore measure both momentum and position exactly from something. And Heisenberg said you can't do that. That would violate the Heisenberg uncertainty principle. So this is called the no cloning theorem. So in your computer, operations are typically irreversible. So if you do an exclusive OR operation and all you have is the result, you can't go backwards and tell me what A and B was. But in a quantum computer, if you have the result, you can tell me what it was before the result. In quantum computers, operations, therefore, must be reversible and have another property I'll explain in a moment called unitary. So in a classical computer, the bits are zeros or ones, but in a quantum computer, we have this superposition that the qubits are both zeros and ones at the same time. So this gives you much more computing power than your computer because you can operate on multiple things at the same time by the quantum operators. In your computer, if you have n bits, that turns out to define a 2 times n dimensional space. So if n is 100, then the total space you're dealing with is 200 dimensional. But in a quantum computer, from the way qubits interact with each other, n qubits form 2 raised to the n dimensional space. So a quantum computer with only 100 qubits has a much larger dimensionality in its space. And here you can see I got lazy. I didn't compute 2 to the n exactly, so I have all these zeros. And I can't underestimate the importance of having computation go on in a larger dimensional space. So to give you a sense of what dimensionality really means, if you took all roughly 7.5 billion people in the world, probably it's a little past that now, and you put them on a line, in a one-dimensional line, as if they were queued up here in Forest Hills in Queens to wait for the Q64 bus, that line would be 4 million kilometers long. But if you put them on a two-dimensional surface, like they were standing on squares of a checkerboard, you could fit everyone in the world in a space about 40 kilometers on the side, which is actually just about the size of New York City. So you could fit everyone in the world standing in New York City. And this is an image of that with most of the people from Asia here in Queens and everybody from Europe in the Bronx. And if you're willing to have people stand on each other's shoulders, then in a three-dimensional volume, then you could fit everyone in the world in a cube that's about 2 kilometers on the side. And this is that cube sitting here roughly in Greenwich Village in Manhattan. So the increase in dimensionality that you get in doing quantum computing is very important. In your classical computer, you can know the computation at each steps. You could get a dump if you want. I used to say in the old days, just because it's a dump doesn't mean it's garbage. And at the end of the computation, you get a definite answer. In a quantum computer, you can't know the intermediate values because if you look, that collapses the wave function and you can't go on computing. And you never get a definite answer. You only get the probability of getting a correct answer. In your computer, the most complex problem you can compute has a name called the bounded error probabilistic polynomial problem. This is a way of categorizing the complexity of programs. That is, as the problem gets bigger and bigger, how much additional memory in the computer or how much additional time will it take to compute it. But a quantum computer, it's been shown 30 years ago, maybe can compute a different class of problems called bounded error quantinomial polynomial problems. And we pretty much think that this class is much bigger than the kinds of problems your computer can solve well. If you're into these classes, people don't think that quantum computers can solve what's called an NP problem, but that's still up in the air a little bit. So this has led to what Pascal has coined the term quantum supremacy, that each qubit has more information because it's got everything between 0 and 1 at the same time. That when we put the n qubits together, they create a 2 raised to the n very high dimensional space. And we can operate on all those qubits and all their different values at the same time. And so in a certain sense, this makes things massively parallel. And it's possible from a purely mathematical standpoint that the problems a quantum computer could solve are maybe a little more complicated than what your computer can solve. So how do we build a quantum computer? Well, we can build a quantum computer out of anything that has a small energy difference, because this is where quantum mechanics lives. It lives at the smallest size things at the smallest energy difference. So anything that has a small energy difference, we can create zeros and ones to make the quantum computer. So this means there's no established single hardware for quantum computers. Many different approaches are being tried, including using little bits of electricity or magnetism or single atoms or small groups of atoms called quantum dots, or crystals that have impurities put into them, or photons of light, or sometimes even the positions of things or the shapes of things in a substrate, which are called topological qubits. So this is an example of that. This is the D-Wave systems in Canada, and here we have a current circulating either counterclockwise or clockwise, and they have two slightly differences in energy, and that creates the two qubits. And this is a picture of what that chip looks like, and here it is inside the assembled machine. And the way to make the chip work, which is sitting down here, look, a whole bunch of refrigerators. So it's being kept really cold in order to work. And why does it need to be kept that cold? Well, if you have any object and it's sitting here and it's in the world that has an environment and has heat in it, then the ball is not necessarily going to stay there. It can use the energy in the heat for the environment to overcome the potential energy due to gravity and jump up to the top of the table. And we can calculate how often that's going to happen. So if we have a baseball and a table that's 10 centimeters high, it's this Boltzmann factor, and the time spent in the top of the table is this tiny number compared to the time spent at the bottom of the table. So if you put the baseball down here, don't bother waiting to ever see it at the top. But the energy difference where quantum mechanics live, where the D-Wave qubits live, is much, much smaller than that. And here, if we use that Boltzmann factor to see how often all by itself the qubit will spontaneously change from a 0 to 1. And we don't want that to happen. We want it to change from a 0 to 1 when we operate on it, not when it just decides to in a random way. So in order to prevent this from happening, this has to be cooled to with roughly 1/100th of a degree of absolute zero. And that's true for all of these systems that use these integrated circuit chips. So this is an overview of the different technologies people are exploring. So these integrated circuit chips where the qubit is an electric charge or an electric field or a magnetic field is being explored by quite a number of companies, including Google and IBM and Quantum Circuits and others. The strength of this approach is that we're really good at making integrated circuits. This is a mature technology. But the limitation of this technology is that when you connect the qubit to the rest of the world, the quantumness leaks out to the regular world, and that's called decoherence. So the qubits don't last very long. An opposite trade-off has been made by companies like IonQ, where they can take a calcium atom and keep it in a very, very strong vacuum and have it and also very cold, and have it separated from the rest of the world. The strength of this approach is decoherence is not a problem. But the limitation of this approach is this thing is now separated from the world. It's much harder to operate on it and do the quantum computations. Another technology being developed by Microsoft, and this is probably the most exotic of all these technologies. And so this has got some pretty exotic names like braiding in space-time and anyons whose statistical properties are in between those of bosons and fermions. But basically what this consists of is a two-dimensional surface with electrical charges on them. And those charges are the qubits. And by moving those charges and interchanging their places, that is the quantum computation. It's a little more sophisticated than that because the surface that they're on is near absolute zero. It's doing something called the quantum Hall effect with crossed perpendicular voltage gradients. And actually, it's formed a two-dimensional quantum gas, and the electrical charges in that two-dimensional gas are 1/3 of the electrical charge of an electron. Another approach that's being done is to use photonics to develop chips that channel light in different directions and create photons and measure them and interferometers and things like that. This is being pursued by a number of companies, Quantum and Tundra Systems, and quite a number of others also. This is good because maybe we don't have to keep these photons near absolute zero, and we can build much more usable devices. So the strength of this system is this has a lot of engineering characteristics that will be very good. Limitation of this system is that we're really good at sending lots of photons down fiber optics, but we're not so good at the technology yet of creating a single photon and measuring it and channeling. So a lot of work is being done on this to improve it. All right, so let me get away from the technology and get to the mathematics and how you actually do computation with a quantum computer. So this is a wave function. It's a combination of things in the 0 state and the 1 state, and it has these prefactors in front of it. And I have a little thing here to remind me, the usual notation is something called the bracket notation developed by Dirac. And it has a lot of advantages to use it, but I'm not going to use any of those advantages here. So I just picked a simpler notation so things will be a little clearer. And as I said before, there's the superposition, that this wave function is both a 0 and a 1 at the same time. And what's called the Born rule is that the square of these prefactors tells you the probability of finding the qubit in state 0 or the probability of finding the qubit in state 1 when you measure it. Actually, these prefactors are complex numbers with a real and an imaginary part. So actually, it's the norm of those numbers. And since all the possibilities, the probability of all the possibilities must add to 1, then the norm of both these numbers squared must be 1. And any operation we do on the qubit must maintain that. And an operation that maintains that unitary nature of the sums of the probabilities is called the unitary operator. And the second thing that's required from the quantum mechanics is that mathematically we're dealing in a Hilbert space, which means all the inverse operators exist. And so things have to be reversible. In a physical sense, this means the Schrodinger equation doesn't know from time. Things could be going backwards or forwards. And this level of quantum mechanics, energy isn't dissipated and there is no entropy. So what can we do with 1 qubit? So here's a representation of that 0 qubit. It's a two-dimensional vector with a 1 here and a 0 there. And the 1 qubit I'm going to represent by a 0 and a 1. And how we'll operate on them is with a matrix. And so you multiply the rows times the column to get the answer, and the row times the column to get the answer. So I have this operation which is called X. We're going to see this is a not operation. So if I multiply this matrix times the 0 operator, so this is X times the 0 qubit, this is X times 0, I get 1. And if I multiply X times 1, which is, again, this matrix times the 1 vector, then I got 0. So this operator X just reverses the qubit. Very important operator is called a Hadamard operator. And it's a matrix that looks like this. And it's got that 1 over square root of 2 here to make sure at the end the probability sum to 1. Now if I do Hadamard on 0, it turns out I get a combination so that the qubit is now half a 0 and half 1. And if I do the Hadamard on 1, I also get a qubit that half of the time will measure as a 0 and half of the time will measure as a 1. But these two are not exactly the same because this one's got a minus sign. We lose that minus sign when we square it and to get the probabilities. But here it exists, and it's called the phase difference between these two. And this can be represented in something called the Bloch sphere, which I don't really want to get into. So we can have two different bases to do the measurement. I'm going to call one this plus basis, which is the one I've been showing you. And if I do a Hadamard operation on that basis, I'll get the cross basis. So what this means is that a 0 measured in the plus basis is going to be half of the time a 0 in the cross basis and half of the time a 1 when I measure it. And similarly, something that's all 1 in the plus basis will be half and half in the cross basis. So the way we measure something affects what we see and how we see what it is. And this is the basis of something that's really useful, which is called quantum key distribution cryptography. So if we want to send a secure cryptographic key from one person to another, we can use the quantum mechanics to tell if an evil person is listening in. Because every time you measure something, it changes things in quantum mechanics. So because of the property of quantum mechanics, we can tell if our communication is really secure or not. And this is one protocol for doing that. This is called the BB84 protocol. And this is cryptography. So here is Alice and Bob. So Alice is going to send zeros and ones, for example, in the plus basis. She can also send ones and zeros in the cross basis. Every time she sends in the plus basis and Bob receives it in the same basis, he gets the right bit. But if Alice sends it in the plus basis and he measures it in the cross basis, half of the time he'll get the wrong result. So the way this protocol works is Alice sends all these zeros and ones and keeps track of what basis she sent it in. Then she sends a message, could be in the clear, to Bob, saying when she used which basis. She doesn't say which bit she sent, but only which basis. And when she does that, then Bob can throw away the bits that he got that their bases were mismatched, and he can keep the other bits. And this is secure because someone, for example, Eve, who was listening in, doesn't know initially what basis Alice used. And if Eve measures in the same basis and resends it, and Bob measures it in the same basis, Bob will get the right answer. But if Eve is guessed wrong and measures it in a different basis, half of the time Bob will get the wrong result. So Alice can send a whole bunch of bits this way to Bob, and if Bob sees there are a lot of bits that are wrong, he knows someone else is watching. And this works because in this principle of quantum mechanics, once you measure something or you measure it in a different basis, you change it. And these networks actually exist. There are installations with these networks in the US, in the European Union, in Switzerland, in China, in Japan, and actually other places too. So this is an off-the-shelf equipment, and this is an active commercial use of quantum mechanics and qubits. And the qubits here are actually photons of light. So that's what we can do with one qubit. What can we do with two qubits? So now when you combine two qubits, this is what I was saying before, the way they combine is called a tensor product. So each piece of one qubit gets multiplied by all of the pieces of the other qubit. So this one is up here. 1 times 1 is 1. 1 times 0 is 0. And 0 times 1 and 0 both 0. So when we multiply these two qubits together, we get now not a two-dimensional thing, but a four-dimensional thing. This is why as we keep adding n qubits together, the dimensionality is 2 raised to the n. So here are the 4 vectors that correspond to the 4 possibilities of these 2 qubits in their 4-dimensional space. So there are a number of different qubit operations. One of them is called a conditional NOT. And what happens here, this operation leaves the first qubit alone, but if the first qubit is a 1, then it switches the second qubit. It exchanges it forever it was. If it was a 0, it makes it a 1, and if it was a 1, it makes it a 0. So for example, C0 of 0, 0 is 0, 0, but C0 of 1, 0, you still keep that 1, but that 1 tells you to switch the second bit, and that becomes 1, 1. And this is what the C0 matrix and operator looks like. So when I multiply this matrix by 1, 0, which is this vector, I get 1, 1. And we can combine other operators too. So this is our friend, the Hedemond operator. If we tensor product that with an identity operator, this is a matrix with 1s along the diagonals and 0s elsewhere. So that's the identity matrix, and we'll get a matrix like this. Okay, so now we put together all the little pieces so we can finally do something interesting. So this is what I'm going to do to be a little more interesting. We're going to use a C0 operator, this Hedemond and the identity operator. We're going to operate on a pair of 0, 0s. When we do that, we get a result here, which decomposes to a set of two vectors, which is 0, 0 and 1, 1. So that means half of the time we measure this, because it's the square of this, we'll see 0, 0, and half of the time we measure it, we'll see 1, 1. One way to represent these operations is by what's called a circuit diagram. So this is, and we're starting with 0, 0. This is the Hedemond. This is the identity operator. This is the C0 operator. It's represented by a dot indicating which bit is going to control the other one, and then this circle, which is the control bit. And one of my pet peeves is, I don't know how many lectures I went to where they had the C0 operator that were never labeled, and I didn't know which was controlling which. And I don't understand why this has got a plus sign in the middle. If it's really doing an X naught, it should have an X in it. But in any case, this is the way it's usually done, and I've at least put the words in. And then at the end, we're going to do a measurement operator. Okay. And again, just to emphasize what we see here, we square this. That says the probability is a half that we measure 0, 0, and the probability is a half that we measure 1, 1. So remember, each of these qubits is a physical thing. It's a photon. It's a little piece of an integrated circuit. So I could take one of these 2 qubits and I could move it to the moon. And I could keep the other one here. And if I do that, when I measure the one on the moon, sometimes it will be a 0. Sometimes it will be a 1, 50-50. But every time I measure it as a 0 on the moon, and then someone else measures it on the Earth, they'll also get a 0. And every time I measure a 1 on the moon, that person back on the Earth also gets a 1. So how do they talk to each other? How does the one that was already measured tell the other one what's going on? And the person who was most upset about this was Albert Einstein. And if you pardon my very bad German, he referred to this as spukhafte Fernwirkung, which is usually translated as spooky action at a distance. The word we use today, more modern word is to describe this, is entanglement. And this is an example of a circle that does entanglement. This is that same circuit I just showed you. This is the IBM system, which you can use to program a simulator or the real IBM quantum computers graphically. And they also have a Python package version of this also. Many companies are putting things online so you can get used to using them. for people to create new algorithms and create a market for these products. So this is the result of running one of the IBM computers, Tenerife, 1K times. And you can see about half of the times it's 0, 0, and half of the times it comes up 1, 1. It should never come up 0, 1 or 1, 0, but it does every once in a while. And this is that evil hand of decoherence tapping on those qubits, because this is in a certain sense an analog computer and it's not perfect. If we run the same calculation on the IBM simulator, it comes out only 0, 0, 1, 1, nothing in between. Never comes out exactly half. Welcome to quantum mechanics. We get probabilities only. And there are more physical situations that you can actually entangle different qubits by doing neat things with lasers. And in fact, this was done about 2 years ago with a Chinese satellite, Nikias, which was put in orbit. In this case, it generated zeros and ones, or ones and zeros. And it was sent down, photons of light was sent down to the Earth through a small telescope on the satellite and a bigger telescope on the ground. And every time one of those ground stations recorded a 0, the other ground station a little less than 1,000 miles away recorded a 1. And every time one of those, one station recorded a 1, the other station recorded a 0. So this is entanglement, and entanglement really happens. And that's good for us because both superposition and entanglement means we can do more things with the qubits than you can do with regular bits. And that leads to the power of quantum computing. And one of the things that has hyped quantum computing is an algorithm developed in 1994 that defeats RSA encryption. And this algorithm, Alice, we're back to cryptography and Alice and Bob. So Alice sends a public key to Bob. Bob uses that key to send a message to Alice that only Alice can read. And this system, the security of the system, depends on the fact that if you multiply two numbers together, two large prime numbers, that's easy. But if just given that prime number, it's much harder to factor it into those two numbers. And that's what you need to do to break the system. So what actually happens, Alice will choose P and Q. From that, she creates N and E and D. And she sends N and E to Bob. She doesn't send D to anyone. She keeps it very secret. Then Bob has a message M, and he uses N and E to encrypt the message. So the way he encrypts it, he raises his message, which are binary digits, to the power E modulo M. And he sends that message in the open back to Alice. Anyone who sees all these things can't read Bob's message, but Alice can with her secret D. What she does, she takes C and raises it to the D power. Remember, she's the only one that's got D. And M to the E times D power is M raised to the ED power. And I haven't shown you how the mathematics of this is done, but it turns out that M raised to the ED power is 1. So M raised to the 1 is 1, and so Alice can read the message. And if you could, given N, you could from that factor it into P and Q, you could read the message too. So the most secure version of this now uses 2K binary digits, which is about 617 decimal digits. And classical computer, the fastest factoring algorithms, would take 10 to the 38 operations to factor this. And no one's going to be able to do that. On the other hand, using a quantum computer and Shor's algorithm, you can factor this in n cubed operations. So this is how a quantum computer could be 10 to the 28 times faster than a classical computer. And Shor's algorithm is very complicated, so I'll just outline it very briefly. It turns out that you use the N to create a function that has a periodicity in it, and you use a quantum discrete Fourier transform to find that periodicity, and then you use some magic from number theory with that periodicity to factor n into p and q. And this is a symbolic quantum circuit of how that would be done. And people have actually done this. So this has been implemented on quantum computers that use photonics, on quantum computers that use isolated calcium ions, and quantum computers that use integrated circuit chips. Now, the biggest numbers people have been able to factor are in the order of 15 or 21 or maybe 35, actually. So this is an important proof of concept, but this is also a long way from actually breaking RSA encryption. There are other algorithms, too, that people have studied for a long time, so that this is a problem where you're trying to see whether a function operating on a 0 is the same or different from that function operating on a 1. And a classical computer takes 2 operations to do this, because you got to do the function on 0 and do it separately on a 1. But a quantum computer, because these 2 things are entangled, you can do with 1 operation. And if you have n input pairs and 1 output pair, a classical computer has to check 2 raised to the n minus 1 plus 1 operations. But the quantum computer, because it's dealing with everything superimposed and entangled, can do it with 1 operation. And there are also some search algorithms that would be faster in a quantum computer. Well, just a little bit reality check on this. Actually, RSA, after 40 years, is being phased out to other encryption systems. But people have been making and breaking codes for the last 3,500 years. So even defeating RSA wouldn't mean that much. People would create a new code. And most of the problems that people developed to show that quantum computers would require much fewer operations aren't real-world applications. But all of this work that's been done 40 years ago has now led to real quantum computers and real algorithms. And this shows that basic research has created new and unexpected valuable possibilities for the real world. So when do real quantum computers happen? Well, in a certain sense, this has already happened, that there's a quantum computing ecosystem. So much money has been put into this in China, more so than the US, in the US more so than in Europe. But this has led to the creation of new photonics and other types of chips and solid-state chips. It's created new algorithms for people to do different things in finding energy minima and machine learning. So it's already led to things that will be very important. In Maria Mazzucato's book called The Entrepreneurial State, she emphasizes that the importance of the defense contracts in the Cold War and spending money to land a man on the moon wasn't landing the man on the moon. It was all of that money and the support of those companies that created integrated circuits and dynamic RAM and hard disks and LCDs and lithium-ion batteries and digital signal processing and GPS and a lot of other things allowed people 20 years later to create the iPhone. And this is actually a list of things that went in one way or another to the iPhone. So the technology of this quantum computer ecosystem is today creating technology that will have tremendous advances further down the line. So if quantum computers do happen, what will we do with them? To go back to the beginning, Feynman said, we can't use classical computers to calculate quantum systems because they're too complicated. But if we could use a quantum computer, which is a better match, then we could do real quantum calculations and better understand molecules to make pharmaceuticals and lots of other things. And if they're good, these quantum computers at solving complex problems, maybe we can solve a lot of other high-dimensional complex problems. in physics and chemistry and biology and social sciences. And maybe we could use that to make better predictions about the weather. And most of the materials we make are either homogeneous or things that are pretty much mixed in at random. But we can design materials with much more structure inside and use quantum mechanics to predict their properties. And maybe we can also apply this to complex networks and patterns of interactions like logistics and social patterns. Right now, groups of scientists are working to try to understand how people network together in order to understand the spread of the virus that's going around now. And there's been a lot of interest in this in fintech, which in the ancient times of 3 years ago used to be called finance. And they deal with a lot of complicated problems, like what stocks should you create in a bag of things together to maximize probability? Or if there were different market scenarios, maybe even including the unlikely one that's happened now, how could you estimate the risk that you were doing in buying or selling options, for example? So where is this really going to go? When is this really going to happen? And what will be the problems that it will solve? Well, it's a little embarrassing for me because I live in Queens and I'm much happier about the New York Mets baseball team than the Yankees. But to quote a very prescient Yankee about this, Yogi Berra, it's tough to make predictions, especially about the future. All right, thank you.
Thank you, Larry. Thank you very much. I've got a couple questions here that came in while you were talking, and some of them were answered by others in the chat. But first of all, what's your view of the Google quantum supremacy paper that came out? I guess it was what, December now? What problem were they trying to solve, et cetera? Can you give us a rundown on that?
That's a real tour de force. They were trying to solve what are the probabilities of a whole set of bit strings, which is one of the standard sort of quantum test problems. I think what they did is very impressive. As whoever asked that question probably also knows, Google said it would take 10,000 years, I think, for a regular computer to solve it. IBM was sure one of their computers could solve it in 2 days. So there's been some controversy over that. So I think it's a very impressive achievement, but I think what I'm waiting for is really the applications to real world problems. And there's a lot of work going on right now in terms of the development of quantum machine learning algorithms that in principle could be much faster than classical algorithms. So I think that's an important step, but I think we're really waiting to see what are the algorithms that are going to solve real world problems.
Well, allow me to toss something in here. That paper itself, if I recall, it was what they were trying to do is really prove that a random number was random. Is that your take on that paper?
No, I think, so I don't remember it in enough detail for the moment, but I think the point was you could have, if you looked at the qubits, many, many different bit strings. And I think the problem was to calculate the probability of each different bit string.
Okay. Another question is, in your experience, have you seen any of the quantum systems ever get close to the promise? For example, D-wave is not necessarily faster than classical.
Right. So I would say in terms of the hardware, all of the systems, because of decoherence and noise and other stuff, are not functional quantum computers. D-wave is an interesting case. It is true it's not a full quantum computer, but it's very good about doing energy minimization. And there are a lot of problems you can solve by minimizing an energy function. So even if it isn't fully quantum, it's still very useful and is using quantum annealing to get to a nice answer. I think people are approaching this in two different ways. So since the quantum computers or noisy, instead of creating perfect algorithms that don't work on a noisy machine, they're creating algorithms that will work on a noisy machine. For example, to compute the structure in molecules that consist of two atoms, or other cases too. So there's a nice interaction going on between people creating algorithms to match the computers, the hardware, and trying to create the hardware to match the algorithms. So we're still in a process of very active development, but the answer is also yes. I can't point to an example where it's done something. Actually, I gave it as an exercise in my class. If you go to the D-Wave site, they have about 200 applications of companies they're working with where this energy minimization thing may be actually really useful. So there are lots of different people are taking advantage of what works and trying to meld different things together to make them work. So I think that interaction shows the field is going in the right direction.
Yeah, and I hope that continues for sure. Another question, I'm going to guess on the context here. I guess you were talking about some gates, maybe the Clifford gates or some Pauli gates. So the question is, are all these operators a direct consequence of work in the Hilbert space, or were they defined by hardware engineers to facilitate the design of a quantum circuit? I guess he's alluding to...
So it's the first way. So all of these things, quantum mechanics lives in a high-dimensional, discrete, usually discrete Hilbert space. So they knew what they wanted to do, what operators they wanted to do in the Hilbert space, and therefore they've designed the hardware to implement those operations. So for example, I haven't shown how this is done, but on the IBM and the other integrated circuit system, the qubits are actually little oscillators, and then you link them to an oscillator on the outside, and the phase of the oscillator and whether they have and the amount of electric charge determines what those prefactors are in the qubits, and then you send in a series of microwaves from your oscillator to change the other oscillator to do what you want in the operation.
I think that's a great question. Again, we've got a visitor coming in 2 weeks where we talk about the quantum stack, and I think we'll get into a lot of that sort of thing. Let me see. Here's one that just came in. Larry, in your opinion, was the China satellite performance primarily a one-off entanglement demo or a scalable tech stack? And do you think it was indeed an actual entanglement moment?
Oh yeah, I think the importance of that experiment is that it shows that entanglement really works over a very large distance. So that's an example of entanglement over the largest distance. And if you read the article, they did a lot of fancy signal processing things. So it's not always a 0 and a 1, and they're doing signal averaging, doing a lot of very fancy things. But the statistics work out definitely that it worked. There are lines which are fiber optic lines in the Netherlands and across China and other places, which are not 1,000 miles, but which are getting bigger. I know a company several months ago was building a line between Manhattan and New Jersey, and so these lines are getting longer and longer, at least on the Earth, and people are using those entanglements to send real information. So I think the importance of that satellite wasn't that we're going to put up a lot of satellites that are going to have do entanglement experiments, but it was a nice proof of concept and the things that are happening on the ground. And people are developing better and better technology to reduce noise and make those circuits better. So that's really happening.
Okay, let me see. Is there a way to explain the Bernstein-Vaziri algorithm in an elementary way? It seems that it can only be understood when you do the math.
Okay, so I've seen that algorithm. So I know there's one of the photonics quantum computers has that algorithm and another algorithm, but I don't remember off the top of my head what that algorithm is. which is a nice way for me to say I probably don't understand it, so I can't explain it in a simple way.
Certainly out of my pay grade, for sure. Let me see. I guess it's Wisconsin has a one-year academic program for quantum computing. Do you know of any others?
There are quite a number of universities that are doing quantum computing things or have startups off of it. I think, I don't remember the names of all the universities doing this. There are several quantum centers that do not only quantum computing, but what's called quantum information science in Austin, Texas, I can't quite think of the name in Canada, in the Plains, the Great Plains region in Canada near the border. And there are several other universities which do quantum information science type things. And there have been federal grants recently to help develop more quantum information centers. So they're sprinkled throughout the country, but I can't give you a list of names.
Now, one of them, of course, is at Harrisburg University.
Right. Oh, sorry. How could I forget that?
We don't want to get commercial on this one, but just for the group out there, this is Terrell again. I just completed the MIT courses. They have a set of 4 online courses. Each course is 4 weeks long. You don't have to do all 4. You could just do one. They're $1,000 a crack. But if you can get that kind of change together, they're well worth it, I think, especially for starting up. I'm climbing up the learning curve. I'd highly recommend the MIT online. I think there's one starting up very soon, but it's sorry.
Are you talking about the 2 that they have for free, or the program that they advertise it, like 2,000 something, or somewhere around here, 2,600?
Yeah, this is the MIT one is the X Pro education series. It's not free. It's $1,000. But there's tons of other
program. The entire 4 classes. I mean, all 4 classes, or per class?
No, it's each one is $1,000. So it's 4,000 for the total. Another one, while we're on that topic, if you don't mind, Larry, I'm just going to put in the chat there a YouTube series by Michael Nielsen, I think it is, of the famous Mike and Ike book of quantum computing. This is a real gem. He published these videos, gosh, I don't know, 5, 6, 10 years ago. So I just put that in there in the chat for the YouTube series. It's quite good. There's lots of other resources out there.
My course on quantum computing for the determined. My name is Michael Nielsen, and in this course, I'm going to explain how...
Oh, somebody's playing it. Cool. Let me see, Larry. For you, is there already a quantum library that can do modular exponentiation? What's your favorite quantum computing library?
I've been using mostly the IBM system, which is called Qiskit, which is a Python package, because you can run it either on the simulator or actually really run it on one of the IBM quantum computers. So, and I've been using that in my classes because people actually get to run it on a real machine. The basis of Shor's algorithm involves a modular exponentiation, and so that part of the algorithm can be done. I think it's relatively straightforward, although it takes a couple of steps to do that. So I think those sort of packages. There's another system, I guess, called QASM or something like that. And there's even like an O'Reilly book or one of those publishers on quantum computers that goes through programming that system. And many of the different companies you'll see in the talk from Rigetti, they've been working on their own system. So many different companies are sort of putting up different different approaches.
Yeah, let me add to that. While you were talking, just for the community, on Pi Day, which was 2 days ago, Qiskit or IBM published a demo on their quantum algorithm for computing pi. I haven't toyed with it, but I'm sure it works just fine. It's so I just put the link out there for everybody to take a look at it later on. But that might be a good starter algorithm in Qiskit.
Right, and also IBM has a series of Jupyter notebooks which have annotation around them and code, so it provides a nice tutorial for doing things also.
Here's another one. Along with quantum computing, there are talks about quantum internet. Are we talking about quantum switches, routers, etc.? I'm not quite sure of the context of that one.
Yeah, so the answer to that is yes, although that technology is still being developed. So the basic deal is that if you wanted to replace the way the internet works now with a quantum property which is called teleportation, where you could send things maybe faster or maybe with a lot more information, but if you do that, you have to replace everything. So you can't have amplifiers anymore. You have to have things, there's a jargon word for what they're called. So you basically have to do things that creates new photons and entangles them and does stuff. So there have been some experiments. I think the lines are a few miles long in different places. Again, I think there's one in the Netherlands and maybe elsewhere, where people are experimenting if they can use some of these quantum properties to create a much larger bandwidth down the internet, but it requires technology that's consistent with quantum mechanics, and that technology is still being developed.
Okay, well, we're reaching 8:13 here on the East Coast. Any other questions before we let Larry go here?
Yeah, this is Jonah. I have a follow-up on the quantum internet. It was me who asked the question. So basically, you're saying that everything that we have in terms of a classical router or switch is going to be replaced by a quantum router. So now, since this is an expensive toy, right, to keep it cool, wondering if that's exactly what they envision, or only at the communication on the fiber.
Well, well, first of all, I want to say maybe. So we don't know whether the entire infrastructure hardware of the internet is going to be replaced. But look, this has happened before. 100 years ago, 80 years ago, IBM really, Bell Labs really improved vacuum tubes. So that made it possible to have amplifiers in the middle of the desert, so someone in New York could call someone in California. And eventually all those tubes were replaced by transistors that were more reliable and used less power and things like that. So we've gone through a series of successions of different types of hardware and how our networks work. So it's certainly not impossible that quantum mechanics may replace the types of routers and connections we have. Maybe that will be effective, maybe not. So I think there are many interesting possibilities in creating a new kind of internet, and I think people are actively studying that and actively thinking what sort of hardware it would involve.
Okay.
But that doesn't mean it happens, but people, I think, are working on that.
Okay. And the second question is, in terms of going up the stack, right, from the hardware to the software, it seems like, at least from what I understood, all these big guys, Rigetti, IBM, and so on, they create their own stack, right? So my question is there any effort to create some sort of a standardization at this level No?
No, at this point, there's no real effort to do that, and it may be too early to do that also.
Okay.
I thought there was, for some reason, the ACM, Association of Computing Machinery, seems, at least in some of their publications, seems sort of down on quantum computing, I think unnecessarily so. And one of the points they've made out is nobody knows what the real technology is going to be. I mean, I went through it in not very much detail, but 4 technologies, but there are many others too. There are at least 10 different types of technologies. So this is all being sorted out. So I think it's a little too early to standardize things because we don't know what the hardware is going to be. And there's also a lot of discussion that quantum computers are good at doing some things and not other things. There's been a lot of talk, for example, from Rigetti, of having what are called hybrid systems, where we have a classical computer do a piece of something, and then the quantum computer doing a different piece, and they talk to each other. So there's still a lot of open issues about how this would be used. So I don't think it's a negative that people are developing different systems. So we just have to see where it goes.
Yes, Ann. I was at a conference, I guess, December, and if you want to check with me offline, there are a couple, there's a small company in Europe trying to, there's lots of players in the ecosystem seeing these little gaps, and they're trying to create like a common language, if you will, that gets compiled into the various different, Rigetti and the IBM machines and so on. But it's not like a large project. There was another company doing that as well. But people are thinking about it is what I would add here.
Okay.
Certainly, and it's an opportunity for all of us if you want to fill that space. I think it would be a great
There we go.
learning exercise. Okay, getting a little. We're on OT here. Larry, any last minute comments before we send everybody off?
I would just say this is an interesting area, and we don't know where it winds up, but it's fun to see what's happening.